Okay, well, let's go on to talk about the second class of transistors. These are called bipolar junction transistors. Okay, they're a little more complicated than FETs, and so you might wonder why we're talking about them at all. It turns out they're very important in the history of the field, and they're still used today for many applications. While FETs are simpler and were actually conceived of first, it turns out that bipolar junction transistors were easier to make. And so they were the first widespread transistor that was made in large quantities, okay, and the first types of integrated circuits. And as I say, they're still used in many applications today. In fact, both FETs and bipolar junction transistors are used widely. Each one is used wherever it's the best choice for the particular application. Well, let's take a look at these. So here, hang on for a moment. Very good. Here, 1 second. There we are. So now we're going to talk about the bipolar junction transistor, which works on rather different principles than the FET. Okay? Here's how the structure of a bipolar junction transistor looks. This is one type called an NPN transistor. There's another type called PNP. They work in much the same way, so we'll focus on this one. There are 3 layers here. First, there's a substrate or a substrate or collector, which is doped N-type. Then there's a thin layer called the base, which is doped P-type. And then there's a third layer, which is N-type, called the emitter. So we have another 3-contact device, only now the terminals are emitter, base, and collector. And the emitter is going to turn out to be the source of the electrons in the circuit. The base is going to control the flow of current between the emitter and the collector. But electrically, this kind of looks like 2 diodes. One between the base and the collector, and one between the base and the emitter. And if you look at the way this is laid out, it kind of seems like there should be no way that you could pass a current from the collector to the emitter. Because, well, if the collector was positively charged compared to the emitter, then this diode would be in reverse bias and no current would flow. On the other hand, if the emitter were more positive than the collector, then this diode would be in reverse bias and no current would flow. But what we'll see is that in such a device, if the base is thin enough that current can flow through the device, this is called transconductance, and the flow of current turns out to be controlled by the voltage at the base. Okay? This is what a physical transistor looks like, all packaged up. Again, this is a very large transistor that might be used for switching on and off power or for a signal. And transistors are sort of interesting. Instead of being a voltage-controlled switch, they actually function like a current-controlled switch. When they're in the on state, a small current applied to the base switches on a much larger current between the collector and the emitter. Okay? So ICE is equal to IB times beta, where beta is the transistor gain, which is normally a big number, maybe 120 or 100 or something like that. Okay? Well, let's see how these things work. Hang on one moment. Oops, I'm sorry. Having a little trouble here. There we go. Okay, here, let's talk about the bipolar junction transistor. So, we're going to talk about the NPN transistor. Okay, one version of this. And schematically, it might look something like this. We have 3 terminals, the emitter, the collector, and the base. Okay? And what we're going to see is that by applying voltages to the base, we can switch on and off a flow of current between the emitter and the collector. Here, let's see how this works. Sorry. Okay, give me a second to make a drawing. This will be a band diagram. And I might have to beg your patience here while I do this. Actually, here, I'm just going to pause for a second while I make the first drawing. Okay, here we go. So we have our semiconductor. We have the three regions, N, P, and N. And of course, in each region, we have carriers. In the N region, we have electrons. And in the P region, we have holes. Okay? And this is how things might look in the state where there are no voltages being applied to the emitter, base, and collector. They're all at 0 volts. Okay? And of course, in this state, no current will flow. Now, what's interesting is what happens when we start to apply a voltage. First, let's imagine applying a voltage between the emitter and the collector. Okay? 1 second here. I have to redraw my picture. I think I'll just pause while I do that. So imagine the case now where the collector voltage is greater than the emitter voltage, but the base voltage is equal to the emitter voltage. Okay? This will be the off state for the transistor. Okay? In that case, the band diagrams will look something like this. Okay? And my drawing is not perfect, but I think it'll give you the idea. So first of all, in the emitter region, it's still N-type. We have electrons. And in the base region, it's still holes. And the barrier between the base and the emitter is exactly the same as before because we haven't changed the voltage between these. On the other hand, we've made the collector more positive than the emitter, which from the point of view of electrons means we've lowered the potential energy there. So for electrons now, the electrons would like to flow from the base to the emitter, but they can't. They can't because there's a barrier between the base and the emitter here. And so this energy barrier between the emitter and the base prevents the flow of current. So the transistor is off. Okay, finally, let's imagine doing the following. We'll keep the collector biased more positively than the emitter as before, but now we'll also apply a voltage in the following way. We'll make the voltage of the base minus the voltage in the emitter equal to the built-in voltage for the diode. And that has the effect of forward biasing the emitter-base junction. Okay? Now things will look like this. Because we forward biased the emitter-base junction, that barrier is now gone, or is small. So that electrons can thermally hop over the barrier. Okay? So now electrons in the n-type region can readily diffuse or drift across into the p-type region, and then some will find themselves then pulled across into the collector. Okay? So now a current can flow from the emitter across the base to the collector. By the way, not all the electrons from the emitter will make it to the collector. A few will recombine as they move across with the holes in the base. So that means that in addition to a large current from the emitter to the collector, actually a current of electrons from the emitter to the collector, there'll also be a small current of electrons from the emitter to the base. These are the electrons that recombine in the base, okay? But the large current will end up being proportional to the small current. And the constant of proportionality, beta, should be much larger than 1 in a properly designed transistor. Okay? So that's how a bipolar junction transistor works. My drawings weren't so beautiful. Here, I'm going to show you one more version of them. Same thing, okay, but maybe it'll be a little clearer. One sec. Okay. Here, sorry. Here we are once again. Here's the NPN transistor in the off state. We have a voltage between the emitter and the collector, but there's 0 volts between the emitter and the base. And so there's the built-in voltage is a barrier that prevents electrons from flowing from the emitter to the base, okay? However, if we forward bias this junction, if we apply a voltage at the base, which is 0.6 volts larger than the voltage at the emitter, then electrons will be able to diffuse across this junction. And when they do so, some of them will recombine in the base, but most of them will continue and be pulled across the junction to the collector, because in doing so, they can lower their energy so much. Okay? And in that way, a small current at the base is accompanied by a much larger current to the collector. And so a bipolar junction transistor, again, works. We can switch on and off a large current between the emitter and the collector by applying a small voltage at the base. Very good. Well, let's stop here.